the value of the source. So what kind of current, draw this, where's H1 go? Over here? Let's say I powered up this control transformer here. 120 volt, 24 volts, okay. And this happens to be a 200 VA. There we go. We've got a fuse in here, but we're not dealing with that stuff just yet. We will be in the code though. We will be doing, by the way, capacitor code, transformer code, and motor code. Not today, but coming tomorrow. No time for it this week. So what's the ratio on this?
It's like 5 to 1.
5 to 1, you sure it's not 1 to 5?
1 to 5.
1 to 5.
5 to 1.
No, 1 to 5.
It depends where your primary is, right? So if the primary is here, what voltage do I have to supply to that winding for it to develop the correct VA when I have a load on it?
120 volts.
You have to match the voltage to the winding. That's one of the key things. Match the voltage to the winding, check. So that's one of the first things. So 120 VAC supplied. That's my supply. I have no load. So now this just becomes a bunch of wire on a cord, and it's an inductor. So that inductor, if this is my supply voltage, and this is my counter EMF, let's do it here. Let's call it the negative EG, right? So as this becomes, if this is negative and this is positive, let's do the right colors. Having fun here. That's negative and positive. Which way will the current go through the primary winding? Left to right, yeah. I'm going to do a dotted line because it's not normally a dotted line. I'm just showing it as that, just to say this is a small amount of current. The amount of current going through this right now is called magnetizing current. It's the current necessary to develop the magnetic field and nothing else. It also has a little bit of resistive component. So because of that resistive component, well, we know in a pure inductor the current lags the applied voltage by 90%. 90%? 90%. So let's call it, let's pretend that there is no actual resistance. Then it would be, if it was the case, the magnetizing current would be actually small. Really small, I'll just do this much. And it lags the applied voltage by that many degrees. And the reason why the counter EMF, or the negative generated voltage countering the supply, is not equal to it is because of a small bit of resistance in those windings. So it says transformers are to some extent reactive. The input power VA is always in VA because you don't want to deal with what kind of a load might be connected to it. So it's the total amps. Do we care when the amps happen? Not really, lagging, leading, whatever. Right now we don't care. We just know, hey, we have that many amps. I measure with my ammeter 100 amps or 10 amps or whatever. That's the number of amps. We don't know when the voltage happening and when the current is happening when you're measuring that? No idea. Other than the type of load that's connected, then you can do some calculations. But for measuring purposes, you're measuring the hypotenuse in every case, right? I don't know what angle that's at. I don't really care. I just need to know that I don't exceed that many amps. So how many amps would it be maximum on the primary and maximum on the secondary in this case?
1.67.
That is called magnetizing current.
Is it 1.6?
This would probably be, by the way, in the form of milliamps. So we just neglect it usually. Okay. So what is it for this one? 200 divided by 120?
1.6?
1.67.
Okay, so maximum 1.67 amps for the primary, or for the high voltage winding. For the low voltage winding, it's going to be 5 times that.
8.33.
8.333, okay. Maximum. What's the secondary winding drawing right now?
There's no load. It's a trick question.
Zero. There's no current. Because there's no connection. So the only thing the supply will see is whatever milliamps. So you have to get a meter that can read smaller current in that case. It'll probably say 0.2, 0.3, 0.4, something like that. I don't think it would be half an amp. It might be half an amp, you know, up to there, but 500 milliamps. It's not going to be a full amp. That would be too much. I connected a transformer one time at a glass place, and I turned it on, the secondary switching, everything was off. The panel that it fed was off. Everything was off. The primary drew 40 amps. And this thing was on it's a small transformer, I think it was a 30 amp breaker. So 40 amps sitting there humming away at 40 amps, and then trips it. So something was wrong with the primary winding. It was shorting out somewhere in the primary, so I had to go order another transformer and have them deliver it. I think it always happens just before a long weekend or a major holiday or something. I think it was a situation like that. It always seems to be that way. When you need the part, you have to rush it in and get it there now, and stay until 8 o'clock at night just trying to get the thing running. So with no load connected, we can consider that voltage to be equal to the source, but it's a small little bit here of voltage is remaining. A small little bit of voltage remains, and that's due to whatever that is. Let's call it EVR, it's a drop. Anyway, or E, it's just, that's what's remaining. So it's going to be a small current, small voltage, small current. So we're going to assume no losses. Volts per turn, so here's your volts per turn, just recapping this. 100 volts, 100 turns on the primary, 1 volt per turn. So when you're establishing the flux around the core, it's wound on the same core, right? So you got primary wound the same as the secondary. Secondary has no load on it. But the changing flux in the primary is inducing voltage into the secondary. If I measured with a voltmeter here, would I measure anything? I'd measure 24 volts, hopefully, if everything was accurate. How many volts per turn would this transformer be displaying?
How many turns?
I don't know the number of turns, so yeah, good question. How many turns do you think are in this thing?
462.
Okay, you picked it. Is the secondary going to have less turns or more turns?
Less or more. 5 times.
Less turns stick away.
Okay.
92.4.
Okay. that's true, how many volts per turn is that? I'm gonna get Michael to do that because he chose the number of turns, so math doesn't work out so nice, is 1 or 1.2.
0.26 volts per turn.
What is it?
0.26 volts.
0.426?
No, 0.26.
My bad, heard it wrong. Volts per turn. Okay, what would it be on the secondary though?
Same thing.
It's the same thing. No?
It's the same.
Yeah.
That was a trick question.
Another trick question.
I'm just seeing what you know, right?
For the ES and the EG there,
Yeah.
VR is just the difference between the two?
It's really because this doesn't match. The angles aren't correct, I don't think, for the VR, but the VR would be in line with, well, there is no resistive portion. There'd be a voltage corresponding with this current as well, because there would be a VXL that would be in phase with the magnetizing current. So, but the VR would be in phase with the supply voltage. The resistance always is, right? Anything resistive is in phase. This horizontal. So that's why I drew it there. The reason why we have a drop is because of the resistance of the windings. Otherwise, if there's zero resistance, this voltage would match. We'd have nothing, no difference. It would match. And you'd have a purely inductive circuit where the current lags exactly 90 degrees. So all I was getting across is this is an inductor. Because there's no load on the secondary, this is an inductor. What it's doing to this conductor here has no effect on the primary unless there's a load. And I'll get to what it does to the primary, but what I'm trying to establish is that there's this magnetizing current. And when you connect the load, we're gonna not look at it this round, but the next round, what happens to the primary when you actually connect a load and what type of load and how that changes. So I'm just step by step. Too much talking, right? Okay, secondary voltage having 120 volts, 1,000 turn primary and 100 turn secondary, so you can use the volts per turn. Just recap of what would be the answer to this, find the secondary voltage. What would you guys say? How many volts per turn is that?
Could you just times it by 10?
0.12.
0.12, is it?
Well, you have 120 volts as your primary voltage.
1.2 maybe? Or is it 0.12?
120 divided by 1,000
You're
is
right.
0.12.
You're right, okay. 0.12, and then so 100 turns times 100.
What?
So the secondary voltage. Secondary voltage.
Sorry, I didn't know how to do that.
So 0.12 times 100.
12?
12. So that's one method that you can solve it, or you could solve it EP over ES equals NP over ES. Efficiency of transformers. You can, I don't know if this is large enough to see, but single phase transformers, the efficiency of, like, say, a 25 kVA, 98%. So what are the losses? Well, you're going to have copper losses in the primary, copper losses in the secondary because of I squared R. You got wire.
A little bit of eddy current.
You've got some eddy current losses, hysteresis losses.
I can't remember the start of hysteresis.
Yeah, and it all develops heat. So the energy is usually in sound, vibration. So all those forms of energy are the losses.
They're loud.
But it's only 2%.
Hey, what are those, this probably won't narrow it down. I had one at my old house, so everything was underground. It just those electrical boxes. The ones that look like they just open right up in the front, you know, big yellow or big green ones.
Oh, like the manhole kind of boxes?
It's like a trigger box?
Yeah, maybe they're like manhole, I don't know what. They
Is
make a lot of
it
noise.
like-
They're huge, though. They're like half the
Oh, he's
size
talking
of
about like
yeah.
his generator.
at your house.
Like those
There was
huge,
just one in my like front yard.
no, it's like a
Just
huge
like a
green,
whole block.
it's like a green box, it's like this thing, well, yeah. It's green, I'm pretty sure it's like.
Transformer.
I'm pretty sure it is, cause it hums all the time.
Is the transformer when the power lines are underground?
Yeah,
Yeah, I used to like jump on those.
It's a pad mount, it's a pad mount transformer.
It's on
Terrible
the big
idea.
So it'd be a distribution type?
Well,
And they have the shock, yeah, the shock hazard.
Yeah. I was
It's all
always
good, man.
just
Just
waiting
jump
for
on
the
it.
lightning bolt to go right through my chest, never happened though.
Relevant to the sticker.
Like that?
Yeah.
And it's on a concrete pad?
Yeah.
There you go. So what
Oh,
they
forgot the
have,
sticker.
what they have underground is the other hydro duct coming in.
As a kid, I was like,
Whoa. So hydro. And the rest is hydro too, but usually they contract it out at that point. And you could go to like 8 houses. So you got wiring going to like several houses. So if that thing blows up, then all your neighbors and yourself lose power, right? So that one transformer can handle all those loads. Michael?
does that transformer go up to the power lines?
Yeah.
And then the transformers on the posts, is that your distribution transformer?
They just come right down the fucking.
On the post. I mean,
Like, on the power lines outside your house, when you
Yes.
sometimes see a almost garbage can looking thing, that's a transformer, right?
Great garbage.
that could be, that is an overhead type.
Yeah.
And that is a pad mount. So this is an outdoor oil-filled pole mount.
Okay, is that your distribution transformer?
Yeah.
Oh,
They're all examples of that. Yeah. All examples of
Take that transformer.
distribution transformer.
Sucks to be you, Neil.
So but what happens sometimes, guys, instead of that, you'll have your hydro line coming in. And then you'll have a pilaster. You've got this sort of metal or plastic, probably plastic, yeah, but it's heavy duty gauge thickness, so that so nobody like chops into it. And so your voltage, so this transformer here, a lot of times this isn't high voltage. The transformer will actually be up here, and this will go underground, and it'll be like a dip service. Right? It's a dip service because it goes down from overhead, but then dips down and underneath. But this one here, if this is high voltage, like out here going to this building, if it wasn't in a pulpit, it could be from the line. You could have 25,000 volts going down here and then feeding the substation, unit substation, we call it, inside a building. It's a dry substation versus an outdoor substation. Right? So there's different ways of achieving where the transformation takes place. It's either on the pole or pad mount. A lot of times this would be, this would be 25,000, or in your neighborhood maybe, I don't know, it's 17.2. There's different voltages. There's different voltages depending on it, and I can't tell you what that voltage is. I'm not going to go up there with a meter and measure it. Right? You have to look at the transformer it feeds and see what the rating is. Now you know what the voltage is.
My,
Yeah.
my neighbor, they had one of those, the pad ones.
Yeah.
And, there's a tree in their front lawn and they started getting, I guess the city saw that, kind of concerned that the tree was gonna start growing into the box. So they're gonna charge our neighbor, a whole bunch of money to take down the cost to take down the tree, remove it.
Yeah.
And then my neighbor ended up finding a 20-year-old picture of city workers planting the tree in their front lawn. So he came out with the picture and told them like, no, I told you I've been here for like 30 years and I never planted that tree. It was city workers that planted it.
Yeah.
So it was just kind
On
of a
his
funny story.
property.
On his property.
They're not supposed to touch your property, right?
Well, long back, I don't know, long time ago.
They do that just,
It was like 20 years, 25-year-old tree.
Unless it was like, you know how when you're building subdivisions, and you have like this much has to be park, and this much has to be roadway and sidewalk.
Like they want
And
to
this has to be,
in every
there has to
street,
be
right?
the right kind of trees, so maybe that might be that
They would
situation.
decide, oh no, we need another tree right here in your front lawn, so they planted one.
Yeah.
But because I used argument with them for a really long time, that no, I didn't, and then he found this old picture that he took of him planting it.
That's awesome.
he's like, ah, we're not gonna take it out, so
Find
I
it
hit
the
my
whole
car
time.
accidentally ran it right over. It wasn't very big, there's still,
So ignoring losses, power in equals power out, or we use VA. So we know that already. Volts per turn, voltage turns in currents,
Use
and
that for
then
the
we don't have to really deal with this anymore. We've dealt with this.
On the test, it should be other quiz. What is the name of the thing that was in Kyle's front yard? Yeah.
Set some different types. Core type. So dual winding, so looking at this, the magical part is the core, because whatever happens to the flux is what's causing the voltage to be induced in the secondary. That's the important thing, is the fact that you have this iron core in proximity to this coil of wire. So a lot of inductance, so there's going to be a lot of ability to generate voltage, BLV, right? So flux, length of conductor, tons of length, and velocity was the 60 cycles per second. It's expanding and collapsing, so that's your motion. It doesn't move, but invisibly, yes, the magnetic field is doing the work, right? Shell type, so they do it in the center.
You won't believe it until you see
H type. Ooh. So if you ever see this, it's just different ways that they're wound around the core.
Is there advantages or disadvantages?
So it's like,
Just design. Sometimes there are advantages. I don't really know them per se. So yes, but I don't know.
Would some of them like cool down faster or something?
Oh, maybe.
I know.
Sometimes it's size and dimension. You know, you're fitting it in somewhere. Like instead of this one, using this one. That one. I don't know.
just get it close to shit.
Secondary voltage, 180 degrees out of phase with the primary. So this secondary voltage I'll draw it on the secondary.
Hey, where's John? Go on. Is it gone, I tried to smart you here. I've been cheating all year.
180 degrees out of phase with each other. The supply, the primary voltage and the secondary voltage. So that blue is the primary and the green would be the secondary. I guess it's a small voltage, so that's 24 volts, right? 24 volts. Yeah.
Is the green the same as the orange EG or is that different?
Because of the volts per turn, and there's less turns, they're the same volts per turn, but because this is 24 volts, I made that smaller. So if you want, I'll label it. This is primary. Let's call it primary. 120 volts supply, right? Source, and generated would be the same out of phase. Is all I'm trying to get at here. And this would be 24 volt secondary. You can't really draw them on the same diagram. Well, you could, but it would confuse the issue. You think you're adding to it. It's a separate circuit. It's generating that voltage. There's no load right now. So all you have, like it says, is magnetizing current. Why is the little doorbell transformer warm, even though you're not pushing the doorbell?
Because you keep it inside your house.
Because the button's broken.
There's a small bit of current in there, and over time, it's created a little bit of heat from the magnetizing current. Yeah. Okay, we'll get into this tomorrow in operation. So I'm gonna, as far as we go with that, we'll get into this tomorrow. Heavy resistive secondary load. Okay. Yeah, we're gonna deal with that tomorrow. Okay, so let's go to our thing here, polarity. Polarity, so what kind of polarity? If I've given this what we call an instantaneous polarity, what does instantaneous polarity mean?
When you stop, like, one
When you stop time,
single frequency, I assume?
Frozen time, right?
Mannequin jump.
Okay, so H1 is negative, so what do we want to make this? We'll make it additive. So where do I put
X1.
X1.
To the right.
diagonal?
Yeah.
Okay, additive.
Well, I think that, like, side with plus side.
So that means that X1 has to be,
Subtracting this like
Big two minus signs.
that. I'm a genius.
is that correct?
Yeah.
You sure?
No, I just said it.
Yes.
That's
that's correct.
Is that what you want?
No.
The odds and the evens have to be the same?
Is that correct?
Yes.
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 Oh,
I'm trying to make you think, right?
So
Messing with you.
You can lead a horse to thinking, but you can't make a horse think. Yeah.
I just showed the last video. You can't make the worst.
You do you, bro. Whatever works for you, man. Dude, I do me. Would be one way to remember.
I wish, I know it makes sense in its head. I wish it would stay.
It won't play.
Yeah.
Or it won't play.
We want to change them.
Multiplication.
Which ones are generally additive and which ones are generally subtractive? Which types of transformers that we considered before coffee, which types are generally in that category?
Is it acceptable to say I don't know? Unit 4?
It's the R way.
Power transformers are additive.
Power transformers and additive.
Because it's going up.
More might.
Subtractive for power.
I might be wrong, right?
Oh.
Usually what? Power transformers?
Subtractive.
Subtractive.
Stop cheating.
Okay.
Michael's bringing up the answers.
And what else?
One good one.
It's like you pre-read or something.
Where is it?
It's right above the drawings.
Oh, there it is. Yeah, thank you.
You wrote this?
See? See?
Okay, and additive, usually additive, right? Distribution. What else are subtractive? Does it mention? Doesn't mention. Instrument transformers. Instrument transformers like these, meant for metering equipment, are subtractive. If you look at them, H1 and X1 are on the same side. I'll pass around the PT. Instrument transformers. So subtractive, also instrument transformers. This is good little trivia, and you know there's going to be questions that say instrument transformers are generally additive, subtractive, none of the above. You know, so just learn them, they're really easy.
Would control transformers also be subtractive?
Control transformers are generally, I've seen them as additive. Yeah, I've mostly seen them additive. It doesn't mention, but this one's additive, this one's additive. This one, I don't know, because the layout doesn't have a diagram. It just says the black is 120 and the white is 24 volts. But it's auto transformer. So I'd say that. So the only subtractive ones would really be power transformers and instrument transformers. Usually.
You just gotta get to the Tuesdays, if you know what I mean.
Seriously, I'm gonna get you.
Oh, it does say that.
that year right now?
The dot, I'm gonna have to keep yelling, so I'm just gonna talk this over. The dot is generally on one side, so the dot's on one side, it means it has the same instantaneous polarity.
And turn up the volume.
So the instantaneous polarity would mean that both sides would either be negative at the same time or positive at the same time. Right? And so if this was H1, this would be X1. There you go. So, yeah, so the dot is another form of doing that, and you'll see that on, you'll see a dot here. Here's a dot. It's a little sticker. So I'll pass this around too. This has a white dot, meaning that this side is the same potential, same polarity as the white wire. So, yeah, so if your current is going this way through the donut, the wire you put through that donut, then the have the same polarity on the white. And that's important for connecting metering together. If you connect all the metering equipment together. So they'll put a dot on the outside of the donut, and then they'll identify which wire that is on the secondary.
Does that tell you the polarity, or just tells you these two are the same polarity?
They are the same polarity
And then you
at
just,
instantaneously. Yeah.
okay, and then you look at H1, X1, or to figure out which is negative, which is positive?
Yeah, a lot of times they won't have H1 and X1. They'll just have the voltages, and they'll have the dots.
And you can do whatever you want with the polarity? Or?
It's AC, right? So, yeah, but you have to know which way the current would be going instantaneously, yes. How do you test a transformer for polarity?
Meter.
It's called the AC voltmeter test. Okay, so I'll draw this one. I'm gonna erase this masterpiece drawing here. Is any learning going on here?
Yeah.
Awesome.
Hey, that's my childhood you're racing on. Unbelievable. That's what my dad just done.
That's why you have pictures.
Later.
I was in that race it a long time ago.
I don't have an iPhone. Yeah,
My dad erased it pretty well.
It's the cost of doing that shit.
Yes, sir.
It's like $10 a photo.
Yeah. I bought one of those from like
Same, I did too. It was rough. That was such a waste of money.
and I know that I got the like I won't have any plus my friend got it from her and she was like dudes.
I could use game.
Are you listening to yourself now? So we're just I don't know, I'm telling you this is personal.
So it's like cool, but then you're just like.
Finding Dory, okay.
Was it really Dory?
I do the same thing.
Yeah.
But I have a two-way system, so.
Here's a transformer we've connected up
I don't.
to the rated voltage that we had available. I had a plug and a cord, and I was able to test this transformer. So I connected it up 120 volts to the 120 volt side. Do not connect it to the 24 volt side. Why not?
Because then it will blow up.
Because then you're going to have a different amount of current on that winding, right? Because the reactance is going to stay the same based on the frequency of 60 hertz, and you're going to have more current, and you probably overload the winding, maybe, right? I think 120 volts it might be safe if you did that, as long as you don't connect anything to the other side, but just don't do it. just don't do it. It might, because the insulation on the windings would be able to handle the voltage, but it's just that current, right? So just always put the rated voltage to the rating of the winding. So I'm gonna choose the 120 volt supply. Now I'm gonna put a jumper wire. I'm just gonna put X and X. So let's say this transformer had no markings on it.
Can't use it.
But I knew which side was the high side. How did I know that?
Voltage.
Because it has voltage.
Well, let's say I took, well, I knew it was 120. Okay, let's say I knew it was, you have to know the voltage. Okay, so I knew it was 120. And then if I measure with an ohm meter, so if I check first, check with ohm meter. What kind of resistance would be on the primary? Maybe I'll do that with you guys. See what you think I should read.
What kind of is
So I'm going to measure, I'll measure this one. This one is 600. Just pick one winding.
like the ohms of the winding?
Yeah, just the ohms. There's no reactance or anything. So let's see. Let's do. This one. There's no jumpers on yours.
Does this just go in your hot? Like it just goes in and out? And then you just continue to hot through. The neutral doesn't go in here then.
I'm getting on the 600 volt side,
Neutral doesn't have to.
Neutral.
12 ohms,
Like you don't, yeah.
11.9.
Secondary.
Around 11.9, so almost 12 ohms on the 600 side. And on the 120 side, I'm going to go between terminals 2 and 5 here. Getting 1.2. So which side's the low voltage side? If I didn't know any voltages, I mean, you should know the voltage, but say I didn't know if it was this, if I had 120 and I didn't know if this was going to be higher, if that was going to be 240, what if I measure a lower resistance before I power anything up? Think about it.
Lower resistance means you're gonna have
Means more.
higher current, so you're gonna be.
Okay, the number of turns. How long is that wire? Shorter or longer? Shorter, so less turns, right? So that'd be the low voltage side, less turns. More turns is thinner wire, many turns, meaning that it's higher ohms of resistance. So a way of just checking your transformers, first of all, to see if they're connected properly, or if they're not burnt open inside. It's a good way of troubleshooting, saying, okay, this winding's good, because I got continuity, but you'll also be able to see by the number of ohms which one is the high voltage side and which one is the low voltage side. Does that make sense? More turns? Okay. Give me any answer there.
I nodded.
Feedback.
Okay. So I checked it. After having checked that, now I power it up. Don't power it up when you're measuring ohms, that's bad. That's
So is more ohms, more current, less voltage?
more ohms, more turns, more length of wire that I'm measuring.
Because it's just copper and copper?
Just the DC battery from the meter is measuring how many ohms that winding is. It's like a length of wire. You're just measuring the length of wire.
So the less turns would be 20, less turns, less ohms, that would be 24 then? Or that?
Yeah. So you know that it would go to lower voltage. Anyway, I know the two voltages. That was a side note. I know the two voltages, but I don't know which one is X1 and which one is X2. I don't know if this is additive or subtractive. So first of all, I'm going to say H1 and H2 normally are like that way, right? So I'm going to label those right away. Looking at the low voltage side, I know that has to be H1 and that has to be H2, unless it was otherwise marked, like we saw earlier. Let's assume that. Now, I'm going to say, okay, which one is which? So put a jumper wire on the one side. And I'm going to get two results here. We have two results. Now I'm going to take my voltmeter and measure across the second high voltage winding connection to the low voltage connection. And what this becomes, it either becomes a series aiding battery or a series opposing batteries scenario. It's like you're analyzing it based on a battery. So if this was instantaneously, let's say, let's do it this way. Let's make H1 positive and H2 negative. Okay? I'm going to either read, in this case, I'll give you the results and you tell me if it's additive or subtractive. That's why they're labeled additive and subtractive. From the AC voltmeter test, you can tell which one is additive and which one is subtractive, because if I add the two voltages, I get 144. If I subtract the two voltages, I'll get 96. So how does that work? Let's say, okay, so if I start at this voltmeter lead to the other voltmeter lead, and I take this and I say, how do I get 144? Well, then that means I have to have a series aiding battery. So I would have to go from like this one over to that one. There's my jumper, and there's my voltmeter. So that's that situation. So then this has to be negative. Or sorry, I did it backwards. The opposite of what I said. Is that right? That's better. So this would have to be negative, positive, negative, positive. So we know that when H2 has the same instantaneous polarity as X2, that has to be X2. The 2's have to be negative, and this has to be 1. 1's are positive. Questions on that so far? Have I explained it, or not well enough? Maybe I haven't explained it well enough. Okay, so what this is the source of the supply. So this is your supply here. This is another supply. That secondary winding. This winding is not a supply. This winding is like a small load. It's like a magnetizing current and inductive load, very small load, to that supply. So I think understanding this at this stage is really important. Which source is this first one? It's your supply voltage. It's the panel, the breaker, the circuit. It's not this part of the winding. This winding is causing the flux in this core to establish a new voltage somewhere to use. We're not connecting anything to it. A voltmeter has a very high resistance, very high impedance. So it's not a load, you're just measuring the potential between those 2 points. You're joining these two together, and as long as you don't connect anything, you're not going to fry anything. It's just your testing voltage. That's all you're doing. It's a way of testing. So this one here, this would be like if I go negative, positive like that. To get 96, what would I have to do? I would have to be positive to negative, right? So this one is the source. Negative to positive, 120. And then I go positive to negative, 24. So I'm subtracting, it's series opposing. And so the voltmeter, I will read the difference. So which one is, if H1 is positive, which one is positive down here? Have to be this one, so that's the 1, and that's the 2. Hey, lo and behold, diagonal is additive. straight across is subtractive. So that's where that comes from. Easy peasy. So what do you call that? What test?
The AC voltmeter test.
Excellent.
Good job, Michael.
Okay, DC inductive kick test is another one. DC inductive kick test. Okay, this one you require some DC. So I don't know, usually we have AC available. It doesn't give you any parameters here, it just says, it gives you polarity, that's it. I don't know about how many volts, you know, how many amps a second, what scale do you put the meter on? It doesn't mention anything about that, but this is the part you just want to know. So, what do we know about DC and inductors?
They don't work very good.
Or they work too well?
No, I think they don't work very good.
Okay, inductors, not transformers.
Oh, I don't think they work very good.
What happens after 5 time constants with DC and an inductor?
It caps it.
So what does the current do?
It stays the same. It increases and then stays the same.
So it blocks right away. So as the current is trying to increase the fastest, the counter EMF is at maximum. So if the counter EMF is at maximum, the first time at zero stage, 0 seconds, it's 0 amps, right? And then after 5 time constants, boom, right? So you're going to reach steady state current, and it's going to stay steady state current. So you got to be careful. You got to be careful not to exceed. So if I use a 12 volt battery on a 120 volt, I don't know, let's say I had, well, how many ohms is this guy? This is, let's say that was 12, and we're going to do what? 2 ohms, let's say 2 ohms. 12 volts and 2 ohms, that's 6 amps. I have to make sure that that inductor can handle 6 amps. So maybe measure the ohms of it first before you do an inductive kick test. And then you want to set your, you want to have a voltmeter that either reads, I don't know, you're going to have a resistor in there maybe? You can put a resistor in there, you got to do something. Anyway, let's do a voltmeter here. Black marker, so this will be the black marker. This will be like the black lead on your voltmeter. And obviously that's red. What do we know about the meter when you connect this to the common and this to red, and we click it to DC volts? The red is the what on the meter? The positive. Okay, the red's the positive. So make sure you connect your meter properly first. Now you got the DC meter connected that way. Pick a side, any side. Put your red on one side, your black on the other, and watch what happens to the meter. So on your scale, if you're able to maybe move the pointer up to the middle portion, you'll see whether it's going to swing one way or the other way. Right? If you have a galvanometer, you can set 0 at the center. Galvanometer has 0 at the center. Or you could use your digital meter. It may not work as well, and you'll see a little flash of a negative on there. You'll know that it's going the opposite way because your DC digital meter might have, you've seen that, right? It just flashes negative or something. So there's different ways of doing that. But if you use their analog method here, and let's use a galvanometer, and we'll say that's 0 volts. And then whatever this is, it's going to develop, if this is a 12-volt battery and this is a 1-to-1 ratio, I don't know, whatever it is, it doesn't matter. We'll get either going one way or the other way. When will we get clockwise deflection? When would that happen? Positive deflection. When would that happen?
They're additive.
Don't think about the transformer, think about the meter. When would the meter go that way? When the red is connected to the positive. If the red is connected to the positive, it's going to go clockwise. If the red is connected to the negative, it's going to be reverse polarity, right? So establishing your meter's polarity is important. So I'll leave that. Does that make sense so far?
Yep.
Okay. So now we've got this here. We've got H1 and H2. So I'm going to do the same as them. I'm going to say, okay, I know that this is H1 because it's on the left when viewed from the low voltage side. And this is H2. And if I push this button, what polarity will be instantaneously established the moment I push down on this switch? As soon as that connects, the instant when the voltage kicks the counter EMF the highest.
Your H2 is going to become negative.
Yes.
Is that just because of the source? Which determines
Yeah.
H2 would be negative?
Yeah, this is the source, so yeah. So all you're doing is that. So your current through here, well, right away it's kicking back a voltage on the secondary and limiting the current, and this current will gradually increase to steady state. So you almost want to just push the button. Maybe I'll Google something and see if we can show you. But this is one way of doing it. So if I get clockwise deflection, then this one is positive and this one is negative. So then what would the designations be for X? Which one would be X1 and which one would be X2? If that was my result. So this would have to be 1, yes? And if I got counterclockwise, I'll do a different color. If I got counterclockwise, yeah, let's do it this way. And if I got counterclockwise deflection, then I know I'd have my polarity reversed, and this one must be X2 and this one must be X1.
Question.
Yes?
So the current, because we know that the current goes from negative to positive H2 to H1, and so so the current would have to flow backwards in the other circuit, right? On the other side.
Yes. Yeah, the current here, let's do the red current and the green current, just to show the two examples. The instant you click this, the amount of current would actually, once the current starts flowing, then the voltage would go back to 0. So just going to sort of pause there for a second. I'll draw the currents in a sec. It'll kick one way and then it'll go to 0. You push the button. If you held the button down, it would do this. You held the button, then you did it again. Say you've reversed it. Do that, and now I let go of the button, right? So the kick is really what it says. It's a kick test. The kick is the counter EMF. So the counter EMF, in the first case, if H2 is negative and X2 is negative, then the current would be flowing this way from negative to positive through the meter, right? And then if the current was the other way, then it would be going 2 to 1, 2 to 1, it would be going that way through the meter. Follow? Who's getting positives and negatives mixed up in your brain?
Nope, it's next to it.
Yeah? Mike?
So the voltmeter, that doesn't act as a source, so it just goes through it from negative to positive?
Voltmeter is your load.
Okay.
So outside the source, the electrons flow from negative to positive, right? This is now a source. The counter EMF The first counter EMF goes this way. In the second
Oh,
situation,
because that's a source, so.
yes.
the negatives are
The second situation, the counter EMF is going that way.
But if we're going with our original statement that negative to positive in the left side, wouldn't it go in the opposite direction? In the right? So in the right, if the current's going from negative to positive H2 to H1, wouldn't the current be going counter in the second or right side? That makes sense?
Okay.
So that is kind
Okay, hang on. The current is going this way
Yeah,
in the source.
Yeah.
In the second situation,
so like
the
if
current
we're,
is still going that way.
but if we're going to switch it over, why would the current be still following it? Wouldn't the counter, would the generator voltage be against it or in the opposite direction?
Yes, but it's all depending on how they brought the leads out.
Okay.
So yes, it would counter it, and it would always go from 2 to 1. So if this is going from 2 to 1, and this becomes negative, then the secondary here would have a negative. Let's do this red example. This would be negative, so that would be now the negative supply. So just what Michael was saying, it becomes a source. So if this is a source, this part here now is a source for that load we call the voltmeter right now, because we don't have an actual load. But that voltmeter, this is like if this is a source,
Yeah.
this would be the negative of the supply, right? If they're using the red one.
Yeah.
If this is a source and the negative was up here, right, then the electrons leave that source and come back. Goes from positive to negative in the source.
Yeah.
Right. That makes sense?
It's, yeah,
More clear?
it's a little bit.
Okay. But you gotta know which is, you've connected your meter and you just connect it up and you say that's the red lead, so if that's positive, then, and if I get positive deflection, I know which one's positive and which one's negative. I know which one's X1 and which one's X2. All you're trying to do is label which one is X1 and which one is X2. That's what this describes. Whew.
That wasn't Jeff at all.
I don't know. See it yet. I think so.
What type of transformer is this? I have two answers for that question.
That's a,
Attractive.
signal transformer?
Okay, so I guess I could have more transformers, or more answers.
Is that a signal?
How many windings?
Those,
One? Two.
Two.
Okay. So if your question says, you have a dual winding transformer, after considering this section, this is not a dual winding transformer. A lot of people think because it has a dual winding on the primary and a dual winding on the secondary, it becomes a dual winding. No, that's a multi-winding transformer. So it's important, like if you get a description of a transformer, dual winding, you're just drawing one of these. One winding on the primary, one winding on the secondary. I'm just trying to, or they call it a multi-coil, multi-winding, multi-coil.
so dual is just regular. For what we know, it's a regular.
It's the total number of windings in the transformer. So this would be multi.
I see.
So I'm just trying to get the description because this is where I see the pitfalls. I've seen this before where it says dual winding and all of a sudden somebody draws one of these. And I say, no, don't do that. This is a dual winding. Okay? Got it? Now we're going to go into what if it has more windings on each side? Well, then you have a new numbering system. First winding would be 1 to 2. Second winding would be 3 to 4. Secondary, the same. 1 to 2, 3 to 4. So one side of the winding, why do they crisscross? I'll tell you why in a sec. Don't always count on the crisscross. Sometimes they're not crisscrossed. And it just makes connection a little more difficult. Okay, but the purpose of the crisscross going 1 and then putting 2 over here and then 3 over here is for ease of connection. Because it's easier to connect series and parallel on these windings if they're put in this way. So it's just how they brought the wires out. So on this one, for example, this one. I don't like this one because it's got H1 on the wrong side, but they do the same thing. They do the crossover.
This H1 always starts on the left.
Yeah.
It's supposed to.
So looking at the low voltage side, usually H1, yes.
And then they do the crisscross just so you have positives and negatives. Is that why?
Sort of, yes, sort of. Yeah, it's true, it's for ease of connection. If I wanted to put these in series, it wouldn't matter which one was where, because I would just join those two together, and then I would have, my power source would supply the whole thing, right? But if I wanted to put it in parallel, well now all I have to do is put little jumper bars. So a lot of times they'll have a little jumper bar and you'll put that on the connection, right? Right, Jacob? The jumper bars? So you take the jumper bar and you go 1 to 3, 2 to 4, and those have the same polarity, yeah. And that's the whole point. And now they're in parallel. So instead of, like, if I could overlap this and say in parallel, if I had another winding here, if they were like this, it would be more difficult. If I draw it like this. Yeah. What if I wanted to put this in parallel and I had it like this? How would I connect this for paralleling the two windings on the primary?
You would have
H1 goes 2 on this.
the 2 to the 3.
All the evens get the same polarity and all the odds get the same polarity as each other.
H1 to H3, H2.
So I'd have to go H1 to H3, H2 to H4. Now I can't put a little jumper bar across because, like, if it's a little piece of metal with 2 screw holes and I mount it on, like, say this one, or this one will have a jumper bar, it'll kind of be a U-shaped thing,
Yeah.
and it'll just go right in there and you tighten the screws down. It makes it easier for connection if they're crisscrossed. That's the whole point. So that if I crisscross this instead, H2 is now there, H3 is just how the wires are brought out. Yeah, let's do it nicer. Make it nicer.
It's just like
Now I just do this, right? So now you can just jumper them together like that, and they're in parallel. So H1 and H2 are connected together, or sorry, H1 and H3 are connected together, H2 and H4 are connected together because of the same polarity. That's the whole point. What if I had
I did see that.
120 volt, I'd have a 120/240 volt primary. What voltage would I be connecting to the transformer with this configuration?
240.
With that configuration? Can I exceed the rating of the winding, voltage rating?
No.
No.
60?
So
120.
2. Line 1, line 2. What voltage should that be?
120.
120, yes. Cannot exceed 120 in that case, if they're in parallel. So each winding is now run in parallel, which means like it's 2 parallel sources, you could say, but it's not necessarily a source. but I've established a flux in the core that will be equal to the voltage rating of each winding, and I can operate this transformer with a little bit higher current on from the supply, but the same current in each winding as I would have if I supplied 240 volts across them when they were in series. So let's take the example of the series connection, and let's see what we get. Same core, so you want to make sure you connect both windings, otherwise you're only using half the kVA of the transformer. The transformer's kVA is based on both windings being used. Line 1, line 2. How would I connect this in series?
Just a jump for 3 and H2.
Here's my jumpers.
Just, we make sure it's not 2, 3.
Okay,
Maybe.
so right here. Excellent.
It's 240.
And that would have to be 240 because in order to supply to supply the exact voltage that the winding is rated for, it would be exactly half its rating, so it's 120, 120 is 240. So yes. So this would be a 240 volt supply feeding this. And you get the same amount of flux produced in both cases. With two different supplies. So that's the purpose of multi-winding or multi-coil transformers, is that you can use different voltages to supply the transformer. You also can have different voltages available for the secondary of the transformer. So that's the whole point. So you want to get the exact flux you need to get the exact induced voltage in the secondary. May not be that exact. Okay. What if this was, I'm going to give you this example.
Yeah.
Okay, I'm going to leave this here and then do the example they have. This transformer is labeled, we'll label it over here. kVA. Okay, there's a difference between the hyphen, or not the hyphen, the slash and the dash. Basically the slash and the hyphen, right? Or dash, whatever it is. If it says something slash something, then it's a multi-winding on the primary, or on the high voltage side in this case.
Oh,
So
man.
2400, 4800, so how would I draw that on these particular transformers? What would each winding be rated for?
Each one
Each one.
on the high side would be 2400.
2400, yes. The lower one. Based on this, the lower one means that there's two windings. That's how you tell. You see the slash, say, okay, there's two windings there. The lower voltage is each winding. When they're in series, the 2400 and the 2400 add up to 4800. So that means you can supply this transformer, in this case, with 4800 volts, and in this case with 2400, yeah. So that's how you understand these notations. And then it says dash 120/240. So So in that case, it looks like the lower voltage side also has 2 windings rated for 120 volts each. And they can get what you can get out of this transformer, you can either receive 120 volts for your loads, or you could receive 240 volts. Or you can make a 3-wire circuit out of it. You could do 120, 240, and center tap this one and call it your neutral, like on the secondary. So we'll get to that. Let's go one step at one time, eh? All right, so 120, 240. So if I draw this, so what's the purpose of having multi-winding transformers?
So you can have different supply voltages.
And
Different output.
there you go. We can't really choose what our supply is going to be. We get what we get. Right? A lot of times. It is what it is. Sake of say.
Yeah. Can I have what?
120, 240, so each one is rated for 120. Am I safe to put that on there? Okay. The way I want you to do these is to look at each winding's rating and not to exceed that winding's rating. It's the best way to do these ones. Because each winding is an individual coil of wire with 2 leads that's only rated for the lower voltage. I could I could use half of this and not connect the second winding, but then I'd only be able to deliver half the kVA, because you're not using both of them. It's like connecting 2 parallel 12-volt batteries and disconnecting one of them. Well, that means I only have capacity for whatever the one battery can supply, right? Instead of both. So many amp hours or whatever battery is. Okay, what if I wanted, let's say I have this one. This one I wanted 240 volts out. This one I want 240 volts. This one I want 120 volts. So how do I connect them in the case of the left-hand example? The windings on the secondary.
How do you want to do 120?
I want 120. Okay, I'm gonna, they're showing them as subtractive. Maybe it is because it's a power transformer, not distribution. I'm gonna make mine additive. And I want to check with you first, make sure I've done this right. Before I move on. Is that correct?
Yes.
Looks like.
Okay,
With
awesome.
Yeah, connect the X one.
So parallel?
Yeah.
Okay. And then, if I want line 1 here, I'm going to go line 1, it's connected this way. Line 1, X1 to line 1, X4 to line 2. Sound good?
Yep.
I don't think it really matters. Not in level 3 it'll matter with 3-phase banks, but we don't care, it's only single phase. Okay, 240.
X2, X3.
Done. Right? So where do I connect the wires to these buses?
1 goes to L1 and 4 goes to L2.
Pretty simple. So what is the kVA of this transformer? This is the same transformer, I've just got 2 different connections. So I've done this, 2 different examples with the same transformer. This same transformer is rated for what?
100.
How many kVA? Sorry,
100.
100 kVA. So 100 kVA, if I write next to here 100 kVA right in the center, that means I have 100 kVA available at my source and 100 kVA available at my load. VAN equals VAR. 100 kVA at my source, 100 kVA. What is the maximum current that line 1 can draw in? So maximum, what is the maximum current for this transformer?
2, 3, yes, 2.
So 100,000 divided by 4,800 volts, right? 20.83 amps.
I said 2.
Yeah, so you
Was lagging.
Is that right? Okay.
I did.
Are you ready for this one? 41.67. Is that right?
Yes.
Sounds about right.
Yeah.
It's gonna be double. 41.6. Yeah.
Okay. Secondary. 120 volts. 100,000 volt VA divided by 120 volts.
It's a lot of energy.
Okay.
1830.
So I'm going to draw it over there because it's not the transformer, it's the load, right? 120 volts and this much current gives you 100 kVA. VAN, 4,800 times 20.83 equals 120 times 8.33 out, right? Same? Check. Now this one, 240, should be half this, 416.67. Okay. How are you guys so far with that?
Okay.
Peachy.
Why do they crisscross the two?
That's just the
Because of the best of thing.
So you can connect them easier, that's all. Okay, last thing. How much is each winding on the primary rated for in VA?
Oh,
How many kVA?
2,400.
How much is each winding rated?
Each winding on the primary.
You gotta divide that by your thingy there, so.
Yeah, it's 49.
49,992.
It's
Okay,
It's half.
or
Or half.
exactly half of 100. So if you have a 100 kVA transformer and you have two windings, each winding will be rated the same. They're going to be 50 kVA each. Okay, so let's go. I'll put it in VA. 50,000 VA each.
Yes, they're not.
That lost me.
Okay, so,
What about the secondary?
it's.
Same deal.
Same.
This, it's 100 kVA.
Yeah.
100 kVA.
Yeah.
On a regular one, so.
Yes.
Because we're splitting this in half.
Yes.
You guys follow now? Does this make more
50
sense?
kVA, 50 kVA.
So a lot of times I'll put the VA in the center between the two because each one is rated for primary and secondary.
If you have 30,
Each one is rated the same.
33,000.
You don't care about
This
the
one?
24.
Same. It's the same transformer.
100.
No, this is the rating.
Yeah.
Okay, after lunch, I'll get into some calculations on this. We'll do like
It's
a
just
little
the
bit of
rating,
example
that's your max.
for you guys. Practice.
Jeff, how's the tweets going?
Good.